It's disease.
Newtons.
I'll stop there. There you go. Or Newton meter. The first thing I heard was Newton per meter. Newton meters. Please put a dot in between when you're doing units like that. Meter Newton also is fine. And this is the reason why you really do need to have the dot in there. That's a meter times a Newton, right there. If I don't put the dot in there, that's a millinewton. Now the M is a prefix as opposed to just another unit you're multiplying. So typically Newton is set first. All right. So 12 Newton meters. What about the direction? How do I indicate the direction?
The direction of the door closing?
Or the torque that's being applied.
Okay.
How would you, okay, first off, what is the direction, just without worrying about this part? What's the direction of the torque being applied?
Down.
Not down.
Oh, it's down.
Forward?
I'm not sure what forward means.
Out. Out.
Yes, which is what you had indicated. Yeah, it's causing the door to basically swing like that, so it's outwards. But I could write out of the board. But surely there's a simpler way. Of course there is.
Did you say the direction was out?
Out, yes. Toward you. When we dealt with two dimensions, we had, I hat one direction, J hat perpendicular to it. That's simple enough. I hat's that way, J hat's that way. But when you get into a third dimension, which is what we're dealing with now, we need to somehow indicate in and out of a page or board or surface. The arrow. Imagine an arrow, archery arrow. If it is being shot towards you, you would see the point. If it's shot away from you, you would see the feathers. So the convention is a dot. This would be out of the page. A little K hat there. If it's into the page, you can do a little cross like that, and I know arrow feathers aren't like that, but that's just the memory I trick. This would be into page. Or board or surface or whatever you happen to have. Scott?
So you're saying it's, am I saying, I'm thinking the right thing, is Newton's out?
So you could write out, or I could just go define K hat as out, and just write K hat.
Okay.
If you are want to write out of board, you could write it out in English if you want.
So if it were into the page, we would have to define it as that.
So if it were into the page, so let's say that the force was in the other direction, which flips the torque, because then that would cause the door to close from our point of view clockwise. Then that would be negative, so I could either keep K coming out like that,
Yeah.
and go negative 12 Newton meters K hat, or I could define K hat into the board and do 12 Newton meters K hat, or write out into the board. This is just basically vocabulary here of how to communicate this stuff. All right, I'm about to add one more twist to this. One is probably, well, I'm about to mention one of the nuisances of this. The only nuisance? If I have a box here that I'm pushing on with a 4 newtons of force, and that thing is going to move 3 meters. What is the work that I've done? This will be the chapter 7 stuff. What is the formula for work?
4 times distance.
So what would be the work done?
Newtons times meters.
I think I heard Newton times meters, so, okay. Or, what else can I write that as?
Joules.
So the work done here is 12 joules, because a Newton meter here is a joule. However, this is not a joule. That is a joule, that is not a joule. Fun, isn't it? Joule is, a Newton meter is a joule when you're talking about energy and work and that type of stuff, but when you start to get over to torque, you can't do that substitution. This is not a joule, that's misleading. So you would not talk about joules of torque. It's just the way it is. All right, questions? I can feel the excitement building.
I'm sorry, you have out of board right there, and then you have out of page over there.
Oh.
Is that just, you can do either one?
Yeah, I mean, typically, I'm used to it being on a piece of paper, so out of
Okay.
page.
Okay. Sorry, my brain just could not wrap around it for a second.
Yeah, page or board or whatever that flat surface is.
Okay,
Probably out of surface into surface would make more sense.
okay.
So to go back on what I was saying, is out always positive and in negative, or could they be flipped? Because
It could be flipped.
That's confusing to me. So
Yeah.
which, on when to know if it's negative or positive?
All right, so just like with I hat and J hat, we can make I hat whichever direction we want.
Okay.
The J hat's perpendicular to it. We can make K hat out if we want, K hat in if we want.
Okay.
It's whatever your mood is at that moment. So if I had asked, hey, what direction do we want to make K hat? Whoever spoke up, it would be that way because that person said so. Now, when you get into the more sophisticated math of it, once with I hat, J hat, and K hat, once you've established 2 of them, the third one is actually set. So you can whatever you want for the first 2, but the third one, it's called, typically use what's called a right-handed coordinate system. And beyond the scope of what we did deal with here. Other questions? All right, so we've done moment of inertia. That's the first 2 questions in the master. I want to make sure I at least hit the basics of it. 3 we've just basically talked about. Centripetal force we've done. I want to make sure I at least addressed all the stuff that's on the master set. Guess I can lower this now. Sorry about that. It's not my intent to drop it. Alright. Occasionally I suffer from vertigo, and so if I trigger another episode, then just have patience and if I don't throw up. I probably will excuse myself. Oh, actually, probably a bunch of people. Anyone know how to do that maneuver to get rid of vertigo? The Embry maneuver? Okay. So if I get another attack, I'm going to excuse myself. There's a silly, it looks absolutely silly to do, but I'm going to go to my office, do the silly maneuver. It should help. But I don't think it's going to trigger it, but just in case, just want to give you a heads up. Now, we mentioned this before, but right now, think about my moment of inertia. Think about the mass distribution and the fact that most of the mass is pretty much centrally located. As I move my arms out, moment of inertia, go up or down? Why does it go down? So as mass gets further out, speed goes lower, right? All I asked was just the moment of inertia.
It increases.
Why? What's the reasoning?
Because your mass is spread out.
At a greater distance is covered.
Absolutely. Not the greater distance covered, it's the fact that there's more distance between the axis and where the mass is. So the more you spread the mass out, the greater the moment of inertia. So as I spin around, I'll start out with them close. Then as I bring my arms out, my moment of inertia increases. And what decreased?
Your speed.
We could do better than that.
Your speed.
Your centrifugal acceleration. Is that what it's called?
Not going for centripetal acceleration. What kind of speed?
Your angular speed?
There we go, that's what I'm going for. Angular speed drops when the moment of inertia increases. Pardon? Inertia in general or moment of inertia? Okay, so objects like to keep doing whatever they're doing. I've done the inertia girl story in here. Okay. So, it'll be on the video probably. There was a reference to my daughter, whatever she was doing, she wanted to keep doing, she didn't want to do anything else. Yeah. So that's basically inertia. It's the idea that an object wants to, that's what an object has a tendency to do, is do whatever it's doing at that moment. Same velocity, same direction, which is implied in same velocity. If it deviates from that, there's some force that's been applied. So the way that you can tell what objects have more inertia is by their mass. Mass is the quantity that you would measure to determine how much inertia an object has. So moment of inertia is sort of the angular equivalent of that. It's basically angular analog of mass, and it's, instead of dealing with how easy or difficult it is to get an object to stop moving in some direction, it's how easy or hard is it to stop an object from spinning. So the more moment of inertia, the harder it is to get something to spin. Thus, I had the red and the blue thing there. The red, the moment of inertia was smaller, so I could whip that thing back and forth. The blue one, moment of inertia was bigger because the mass was spread out, so it's a lot harder to do. Is that? Yes?
When does angular speed drop again?
When the moment of inertia goes up. Or we could also say the magnitude of the angular velocity. Not just angular speed drops, but the magnitude of the angular velocity drops. All right, so if we think about it, if my arms are out like, let's see, I want to start inside. All right, so as I'm spinning around, sorry, at some point during this, I get stuff backwards in my head, so Let me make sure I say this right. Yeah, find it easier to explain out. So if I'm going out like this and I bring my arms in while I'm spinning, I should speed up. And just a quick demonstration, start out, I bring my arms in, I speed up. Okay. So as my arms are out, let's think about what I'm doing there. My left arm here, if I'm spinning this way, all I'm doing with my left arm is just bringing it towards me. So as this spins, I'm just bringing this towards me. I'm not swinging my arm wildly, all I'm doing is just bring my arm in. This arm, on the other hand, if I'm spinning around like this, I have to swing all the way around. And that extra push, so from a force point of view, I'm applying extra force in the direction I'm spinning, and I go faster that way. Taking the arms out is the reverse of that. So this is all summed up in what's called conservation of angular momentum. So we have three conservation laws. We have conservation of energy, conservation of momentum, conservation of angular momentum. The symbol for angular momentum, because again, who wants to write out all those words when we just do a single letter? The symbol for it is a capital L. Sort of breaks from the using Greek letters for rotational things. And just as regular momentum, or momentum, is mass times velocity, angular momentum is the analog. The analog of mass is moment of inertia. The analog of velocity is angular velocity. So I've got this I omega, and omega, not a W again. Conservation means whatever I start with, I'm going to end with, assuming it's a closed system. So I have my, let me write up higher on the board. L initial is equal to L final. That's just saying that whatever angular momentum I have initially, I have the same amount at the end. One of the formulas is the moment of inertia times omega, so this is I times omega. Initial is equal to that product final. So I'm spinning around, I have some moment of inertia, I'm spinning with some angular velocity. And so when I changes those, so if this is say 5 and this is 3, if I change my angular momentum so that I have a bigger moment of inertia, so if I make that 10, what happens to how fast I'm spinning? So if I double my moment of inertia, what happens to my angular velocity?
Just slow down.
Yes.
By how much? Did you calculate it? What you get? Yeah. So if this is double, the other gets cut in half. In whatever units that is, radians per second, revolutions per minute. So that was it for angular momentum. It's figure skating is the place where I see it the most. I guess you also see it with divers. When they first jump off a board, they tuck in real tight, so you can get a lot of spins in, but before they hit the water, they straighten out, increasing their moment of inertia, and they spin a lot less. Well, I guess it depends on how good they are.
So what's the unit for that?
So the unit, what's the unit of moment of inertia?
Joules?
No, not joules. Yes, so this is a kilogram times meter squared, and then angular velocity, or angular speed, is basically have the same unit.
Radius squared,
Not,
or,
I heard squared, there's nothing squared.
Radians over seconds?
Yep, radians over seconds. All right, so that's the units that you're multiplying together, kilogram meter squared times radians per second. Radians typically, when you start multiplying it by things, generally it's not written, so this is a kilogram meter squared per second. And that's the unit. There's no nice single word unit for it.
How do you do 1.5?
All right, so I just made up these numbers right here. I said you start out with 5 units of your moment of inertia, and you're rotating at 3 radians per second. You double the moment of inertia, so basically, if angular momentum is conserved, whatever I have to begin with is what I have at the end. So what I start with is 15 units, 15 kilogram meters squared per second, and I end with 10 times whatever omega is,
Oh,
and just divide by 10. Or if you recognize that my moment of inertia was doubled, the other one gets cut in half.
okay.
What if it was the reverse?
If my moment of inertia got cut in half, what do you think would happen? Yep.
Okay.
All right, number 6. Then we get into, so 6 and 7 deal with gravitation, then